So, as always, I'm just gonna go over the worksheet. If you have questions or an answer to something I ask, feel free to say something. I might end up splitting this question up over 2 pages, I guess, because there's not a lot of space. So I made the questions based off the study guide he posted, and one of the questions was about radical mechanisms, or one of the things on it. So I put this as a bit of review for that. There are 3 steps for the radical pathways. The first step is initiation. It's where you form radicals. So H nu is light, it's photons, and that excites the chlorine to make the bond break and form 2 chlorine radicals. This is a radical. This is initiation. And now that we have radicals, it can react with what we want it to and form some products. So here we're gonna react with one of the hydrogens on that specific position just because that's where I showed the chlorine. It's not the only place that it could react. So now we get this radical, HCl, and another reaction that we can get is this. Just gonna put the arrow going down. So both of these second reactions that I've written are, there's really not a lot of space, so sorry about that. These are propagation because we take one radical and we react it with something that's not a radical to propagate the radical to form it on a different species. And you might want to take a screenshot if you haven't copied all this down or you didn't have it all, because I'm gonna erase it so I can finish number 1. So the last step is termination. It's just all the radicals that we have combining with each other. So there's 2 chlorine radicals combining. Here's 2 of the alkyl radicals combining. Again, that's termination. So this is old stuff, it's review. So hopefully this is familiar to you, but it looked like he might ask a question on it based on his study guide. That's why I brought it up. And even if it's not on your third exam, it probably will be on the final in some form. So it's good to understand this. So number 2 said to draw all the monochlorinated products you'd expect to obtain from radical chlorination of 2,3-dimethylpentane. So it didn't give you the structure, but you should understand nomenclature and be able to draw it. So pentane is 5 carbons long, and then 2,3-dimethyl. That's the structure. So monochlorinated just means we add 1 chlorine, just like that first question. And there are multiple positions it can add to. I need to draw these smaller to save space. So I'm just putting chlorines on every single unique position right now to show all the different products. Yeah, that's all of them. Okay, so I didn't draw one with the chlorine here because that's the same as it being here. If you named them, they both have the same name, so it's the same molecule, so that would be kind of redundant. I also asked to rank the relative abundance of each product, so does anybody have an idea of how we can figure that out? Which ones are going to be more abundant than the others? Because this was something on the study guide that when chlorine is at the most substituted position. Yeah, and why is that a rule that we can follow? Um, kind of. So Markovnikov is usually relating to like alkene reactions and carbocation stability, but what kind of reaction are we doing here? Like, it's the same conditions as that first reaction. So what kind of mechanism is it following? I'm just going to go ahead and label these though. It's a radical mechanism. We're using light H nu, so it's a radical mechanism. You also said that in the question. And Markovnikov's rule was followed a lot of the time because the more substituted cations were more stable than the less substituted ones, and radicals have the same stability trends. So the more stable radicals are going to form faster, and they're going to be the ones that lead to products. So because they form faster and react faster, you get more product. So that's why these two tertiary products are the most abundant, because they formed from the most stable radicals, so they forms the fastest. And then the secondary one would be, I guess, second most abundant, and the free primary ones would be least abundant. If he asked the question where he asked you to rank the abundances, I doubt he'd have like 6 possibilities, because this is kind of tedious to do on a test, but hopefully you understand that the radical stability is what caused the tertiary ones to be forming the most, followed by the secondary and primary. Okay, so what kind of reaction is this going to be? What kind of products can we expect from this before we start going over it? BR on allylic positions, yes, thank you. So allylic is referring to the position next to the double bond. So we have an alkene here. So this position is allylic, and this position is allylic. This is also allylic, but it's the same as that other methyl group. So I'm not gonna worry about that. It's just a lot of extra work. So again, just like the first two problems, we have H nu, that's a photon. That's whenever you see this, that means that the mechanism is radical. So like basically an intermediate that we're gonna see is a radical, and then that will react with a bromine to form a product. So like that's the kind of thing you can expect as a sort of step. You don't have to show this if you were taking the test, but that just explains why it goes there. And the specific radical forms because allylic radicals are more stable than other kinds of radicals because they have resonance with the double bond. So just like number 2, where we were ranking the abundance of the products based on the radical stability, this is the primary product for one of them with this reaction because the allylic radical is more stable than like if the radical was over here, that's not allylic, it doesn't have resonance, so it's not very stable. So the more stable radical led to the major product. And another intermediate, like with the other allylic position, would be this. So that would react with a bromine. And lead to this product. So we have 2 products with the 2 different allylic positions. Are there any other products I can draw from this? Resonance maybe, resonance yes. So I will redraw this. So again, this is an intermediate with a radical, and you can draw a resonance form like this with the radical going towards the double bond and then one electron from the double bond, forming a new double bond with the radical and the other electron going to this atom here at the end of the double bond. Shouldn't have put that there. So now we have a double bond here and the radical here, and that will react with a bromine to yield this. I'm running out of space, so I'm going to erase this stuff up here to keep the products. So the other allylic position has a radical that can also have a resonance form. Not supposed to be a resonance arrow. So now we get this double bond and this radical. I guess I'll just draw it going up here. So we have 4 products and they'd all form in decent amounts. So if you have a question where you have an alkene reacting with NBS and H nu, or if you're light, then you're doing allylic bromination. So you should add bromines to every allylic position, like we did for the first 2 here. And then you should consider resonance with the allylic radicals and like draw those resonance forms and then see where the radical ends up, and then the bromine will end up there too. And there are, I'm just going to point this out even though it wasn't a question. So when you have these conditions, you keep the double bond and you add a bromine to the allylic position. But there's another reaction that uses NBS. I don't remember if ether is around, but I know NBS and water are at the very least. So this set of conditions reacts with the double bonds directly to add alcohol and bromine. So even though they both have NBS, they have very different products. So just try not to mix these two up. Remember that the H nu is referring to a radical mechanism. So you have the allylic bromination, and then NBS in water is basically just another way of writing this, which is similar to a reaction where you're adding Cl2 and water to the alkene. And this is all old alkene reaction stuff. You're going to have to know all of that for synthesis questions. That's why it's very relevant to be able to distinguish between these. Oh, well, I already started putting it. I forgot that was the question. That wasn't given. Okay, so question was, how do you get from the substrate to that product? When would you use HCl and when would you use SOCl2? Well, that's kind of what this question is getting at, so I'll answer it when we get to other parts of it. But we're using HCl here. So when you first learned these conditions for turning an alcohol into halogens, you didn't know about SN1 and SN2 mechanisms, but now you do. What kind of mechanism is this following? You should be able to figure that out. What kind of substrate do we have? Yes, SN1. So the substrate's tertiary. The nucleophile is an acid. So it's acidic, it's neutral, it's weak nucleophile. And then the solvent doesn't particularly matter. The substrate's tertiary and the nucleophile is weak, so it's SN1. So now you know this reaction is SN1. For the next question. What do you all think we should use for this? Yeah, so we have a secondary alcohol compared to tertiary, which is what we had before. So if you have secondary or primary, you're gonna wanna not use the acid as the nucleophile. You're gonna wanna use whatever alternative it is. Like here, for bromine, it's PBr3 and ether. And we use this instead of an acid because this mechanism is SN2. It's, yeah, so I have to look it up, but I can show you guys if you want to see the mechanism. The PBr3 basically transforms the alcohol into a better leaving group, just like the proton here would transform it into a better leaving group. And then a negative bromine attacks from the back, so it's an SN2 mechanism. That's in the lecture notes for your class somewhere, so you can look for that. But this with PBr3 or SOCl2 is SN2. And SN2 doesn't work with a tertiary position. That's why you wouldn't use this on a tertiary position, but you can use it with secondary and primary. Here. would we do this? I'll go ahead and start putting this. Yep, we have to use organo copper complex. So CH3CuLi, and you should do this in an ether solvent. I think the solvent's kind of important here. So we just have two methyl groups attached to a copper, and then one of those methyl groups just replaces the halogen. And that's this methyl group here. That's all it was. So that's not too bad. This is one of the only reactions you know that can add carbon-carbon bonds. The other one is the acetyl analyte reaction, like something like this, just a negative charge on the end of a alkyne. Those are the only two you're going to see on this exam, as far as I know. So if you see a new carbon bond form, you should consider this or what I just brought up. What should we use for this reaction? I guess I'll erase this. How can we convert this alcohol to that chlorine? Yeah, we have a primary alcohol, so we're going to want to do an SN2 mechanism, not an SN1. And to get it to be a chlorine, we use SOCl2, and the solvent, which isn't as important, but it's pyridine. What about this? How can we do that transformation? Yep, we have a tertiary alcohol. So we're going to want to do an SN1 mechanism. So to do that, we're going to want to use the acid dinucleophile, HBr. So it's not really a way for you to tell me what the reagent is unless you named what it is, but this is a bit of a annoying question. I don't know if you'd ask exactly something like this, but he could give you the Gilman reagent and then ask you to figure out what the alkyl halide was. Just something a little easier than this. But we have two of these things here. This is the Gilman reagent. So we know that we're adding this and it's going to react with an alkyl halide to form a new carbon-carbon bond. So if we figure out where this is in the product, which is just right here, then the alkyl halide is just going to be the rest of the molecule, and then the halogen is wherever this linkage with the thing that came from the Gilman reagent attached. So it's just this, because when you're reacting with the copper complex, you basically just break this bond and then add the carbon that's attached to the copper in that place, and then whatever else is there. So if we did that, then we'd get this from the Gilman reagent where the chlorine is. So that's the answer to that. Hopefully that makes sense. So you should understand both like reacting an alkyl halide with Gilman reagent. If the Gilman reagent was on the arrow, maybe he could give you this and ask you to figure out what the alkyl halide is. I think both would be reasonable to ask. Okay. I don't know how much he stressed this in lecture, but considering it came up on the study guide, I'm assuming he talked about it at least a decent bit with reaction coordinate diagrams. So basically these were the ideal conditions for this SN2 reaction. And it's good for SN2 because we have a primary leaving group, we have a strong nucleophile, and a aprotic solvent. So those are all things that will favor an SN2 mechanism. And just to ask you guys, do you think we'd also have E2 happening with these conditions? Why not? You're correct. Okay, that is part of it. Yeah, the solvent is aprotic, so that will favor SN2, but there's also something about the nucleophile we're using that is good for SN2, but not for E2. The base is not strong, yes. Cyanate is a strong nucleophile, but a weak base, and you need a strong base to do E2 because part of the E2 mechanism is taking a proton. That's what bases do. So it's not good at taking a proton, but it's good at using its electrons to like kick the OTOS out. And another strong nucleophile but weak base is I minus. These are basically the only two you're going to see. So if you want to memorize that, go ahead. This is the same pattern. It's not what this question is asking, but that's something you need to know. So there we go. Something to keep in mind. I'm gonna erase these things so I can draw the reaction coordinate diagrams. There's energy on the y-axis and progress on the x-axis. It's not going to be perfect, but it'll be good enough. So what changed here with these conditions? We had acetonitrile as our solvent before. This is aprotic. What kind of solvent do we have here? It's a polar protic solvent, yes. So it's methanol, which is protic, and protic solvents are not good for SN2, they're bad. If you don't know why, I can explain it because if you're wondering, but this is still not gonna turn to E2. Well, that's not what we're considering for the question. We're just considering how the reaction coordinate diagram will change for an SN2 reaction with these conditions. So because it will basically be no reaction probably because we still have the weak base, but now we have a protic solvent that would slow it down. So it's not going to be a very fast reaction. But that's not what we're worried about right now. We're just worried about what's going to happen to the reaction diagram here. So we're gonna, well, it's good to be able to identify some things. This at the beginning is the reactants. The peak here is a transition state. And then the ending is products. So I guess I should describe why it'll be what it is. I'm gonna erase this to make myself some space. Okay, so when we have a protic solvent, it's protic because there's a hydrogen on oxygen, nitrogen, or sulfur. We have a hydrogen on oxygen, and that usually means that it can do hydrogen bonding or ion, like it can form interactions with other things. And a lot of the time, those other things have like partial charges or full charges. So, like, say we have cyanate in solution, and then you have like the hydrogen kind of sticking out from the oxygen, and it can interact with other oxygens and methanols, but it can also interact with the cyanate here. That's what these little dashed lines are. And there's going to be a lot of this happening. And these interactions basically stabilize the negative charge. And by stabilizing it, hopefully you remember from back when we were talking about the strength of acids and bases, like the more stable things were, like with resonance forms, the less reactive they were. So that's why protic solvent isn't good for SN2, because the protic solvent will stabilize the negative charge. And because it stabilizes it, and remember this is one of the reactants, so it's stabilizing it. When things are stable, their energy decreases, so we're going to have lower energy reactants, but it's going to go to the same transition state. So because of the protic solvent stabilizing the nucleophile, it's lowering the energy of the reactants. And same transition state. The distance, or like the, yeah, I guess the distance between reactants and the transition state is called the activation energy. And you can see that it increased when we switched to the protic solvent. So because it increased the activation energy, that means it slowed down the reaction, because the greater the activation energy, the more energy it takes to start, so the longer it takes. So yeah, I saw this on his slides, and he probably explained this at least once. The stabilization causes this, so I think you should be able to recognize that. In terms of your test, he might just ask you to like match this set of conditions to how it affects the reaction coordinate diagram. So if you just want to memorize that it lowers the energy of the reactants and then it has the same transition state, that probably works. I don't know what this test is going to look like. I'm just trying to guess and help you prepare. So that's the first part of this question. As always, if you have any questions about something I'm saying, feel free to stop me. So what changed here? At the beginning, we were looking at the OTOS being on this position where it was primary, but now we have it switched to a tertiary position. We're still looking at an SN2 reaction rate, so tertiary is not good for SN2, and we can kind of see why in the reaction coordinate diagram. So does anybody have an idea of how it's going to change it? Transition state is higher, yes, because the mechanism is the nucleophile doing a backside attack. And there's no intermediate like in SN1, but there's a transition state that forms that I'm not gonna draw the whole molecule, but these are all different R groups. Some of them are methyls and the other is an ethyl in this case, but I'm just abbreviating them. So we have a transition state where both the incoming nucleophile and the leaving group are both kind of attached. That's what the dashed lines are showing. They're kind of attached and kind of not. I'll put this to show it's a transition state. But like when we have so many different things attached, like at a tertiary position, then that makes it pretty unstable because there's a lot of stuff surrounding this carbon. It's all getting close together. There's a lot of steric strain. So the steric strain will increase the energy of this transition state. So we're going to have the same energy of the reactants because nothing else changed, but because it's a tertiary position, we're going to have an increased transition state energy. This is just a rough sketch. It probably look better than this, but you can see that this is the original activation or the original transition state, and this is the new one. So again, the difference between reactants and a transition state is the activation energy. And it should be pretty obvious that the activation energy increased for that new transition state because the transition state has higher energy because of steric strain here. So you should understand that. Also, if I'm going too fast, you can just tell me to slow down. I really don't know. I can't tell you. All right, so what's different about this? Originally we had, nucleophile. We had cyanate before. Now we have acetate. Is this a good nucleophile? It does have a negative charge on the oxygen. But is it a good nucleophile? No, because we have negative charge, but we have resonance that stabilizes the negative charge, so it makes this a weak nucleophile. So this would be the original. What's going to happen once we have a weaker nucleophile? What does it mean to be weak? Does that mean it's more reactive or less reactive? Less reactive. So what does that tell us about the energy of this? Is it higher or lower? Lower, yes. So we're going to have, again, the nucleophile is a reactant. So the reactants over here on the left, they're more stable, so they're going to have lower energy. It's reacting with the same substrate, so we have the same transition state, but again, like this is OG, and that's the new one. So we have, it looks exactly the same as when we had the product solvent, basically, because the effect is the same. So weaker nucleophile equals more stable, means lower energy reactants, but same transition state, so increased activation energy. So slower reaction. So hopefully the logic that I've used to explain all three of these has made sense. The only other one is the leaving group. So if I replaced this with like hydroxide, and because it's SN2, hydroxide's a terrible leaving group, that would just, I believe that would increase the energy of the products. Don't quote me on that. I might be wrong. I'm just kind of guessing, but I know it's in your lecture notes somewhere. I just didn't go over that because I think that's the least likely one to ask. I think these three are probably more likely. Again, I might be wrong, but I'm just guessing kinds of questions he's going to ask. Okay. So this is number 6, and I said that this isn't the only substitution products that will form. I asked to show how all the other substitution products will form. So how are we gonna get substitution products besides this one that's obvious because it just replaced the leaving group with the nucleophile? Methyl shifts, yeah, and hydride shifts. So to be able to figure that out, the first thing you would do is figure out what kind of mechanism are we using to do the substitution. We have a secondary leaving group. I actually didn't mean to do this, but it's next to a quaternary position, so it wouldn't be good for SN2 because of that, but it could still theoretically do E2. But the nucleophile acetic acid is an acid, it's a weak nucleophile. So because of that, it's gonna be better for SN1 and E1. We're just worrying about SN1 because I'm asking about substitution, but they would both occur. So in an SN1 reaction, the first step is always the leaving group leaves, or if it's hydroxide, it gets protonated and then it leaves. and when it leaves behind a carbocation. So if we wanted to get this product we have here, the nucleophile would just attach to the carbocation where it is, and we get a product. But if we want to get some of the other products that we can form, we can do a methyl shift or a hydride shift. So we have a secondary cation. The position below it is tertiary, and there's a hydrogen on it. So if we just take the hydrogen and its electrons and push it towards the carbocation, we get a hydrogen here, cation here, and this is a tertiary cation. So this is a hydride shift. We went from a secondary to tertiary, we formed a more stable cation. And this can only, like a hydride shift or a methyl shift, will only occur if it forms a more stable cation. So if this, at the beginning, had been a tertiary cation, this wouldn't happen because it doesn't just go from tertiary to tertiary. That doesn't form a more stable complex. So that doesn't happen. So just keep that in mind. You're not going to get a methyl shift from a tertiary position. But once we have this product, it can get attacked by the nucleophile. You'd end up with this. And I guess I'll just squeeze it in down here. Again, from this carbocation, we can do a methyl shift. So we can take the methyl group up here and push it towards the carbocation. So methyl shift. So now we have a methyl group here, a new methyl group over here, and then one here. Now the carbocation has moved. It didn't stay in the same position. It moved. So just there's a lot that goes on when you do methyl shifts. So try to keep track of everything. If you move the methyl group, then you're going to have a proton on the position where it left. And you also have the methyl group in a new position. Don't just move the cation or just move the methyl group and keep the cation in the same spot. I think that's a common mistake. But once we have this new tertiary cation, it's more stable, so this can happen. Then the nucleophile will attach. So we get this product. So we have 3 products, and 2 of them formed from hydride and methyl shifts. Now, synthesis problems, I basically just use the same exact format of questions he put on his practice, because I'm assuming this is going to be the kind of question you see on your exam. Right, so for this, we're just looking at each step, and if you can't figure out what the product of one thing is, then it's kind of tough to figure out what the next few arrows are. So we'll just go one at a time here. What kind of product are we going to get from this reaction? We have an alkene and BH3 anti-Markov-Markov alcohol, yes. So when you have BH3 in step 1 and then hydrogen peroxide and base in the second step, you do anti-Markov-Markov alcohol addition. So remember, Markov-Markov is referring to a more substituted product. We have a secondary in the primary position. So anti-Markov-Markov means we're adding the alcohol here at the primary position. So this would be the product. And what is this going to do to this substrate? Replacing OH with a bromine, yes. So this does SN2 mechanisms, and we have a primary alcohol, so that fits well with what we have. So we just switch the alcohol out for a bromine. I should have put a sodium here, but I didn't. But it's basically the same. What is this going to do? Well, it is going to be an SN2 mechanism, yes. So we have our nucleophile, the acetylide ion, and we have our leaving group. So it's just going to attack carbon with the leaving group and do that. And we only added 2 carbons, so here's 1 and there's 2. So again, like I always emphasized in the past, you should make sure to count your carbons. You have 2 here, and we have these 2, which are here, and then the 2 carbons from the acetylide. So that's fine. Okay, and last step. Whoops. What will these conditions do to an alkyne? We have mercury sulfate and then sulfuric acid, water. Don't remember. That's okay if we don't. It makes a ketone. You don't really have to worry about the mechanism for these. In fact, for synthesis problems, you don't have to worry about the mechanism at all. It just helps you explain why the product is what it is if you need to explain it to yourself to justify it. But when we have a terminal alkyne at the end of a chain, and we use this set of conditions, it leads to the Markovnikov carbonyl group, so we get a ketone. If we used these conditions with an alkyne, we'd get an aldehyde because it does the same kind of thing as it does with an alkene. It adds a carbonyl to the anti-Markovnikov position, which would be here, which would just form an aldehyde. So that's not what this question was asking, but you should know the difference between the 2 reactions we can do to oxidize alkynes. We can get a ketone or an aldehyde, depending on what we use. How can we do this first step? Why keep going? So that would, it's similar, it has mercury, but we use HTSO4 when we're reacting with an alkyne, a triple bond. This is an alkene, a double bond, so it doesn't use the same exact conditions. But you're on the right track there. the reagents involved, yeah, it has mercury. So the hydrogen peroxide, H2O2, is part of the BH3 reaction. So it's what Michael brought up. It's a two-step process. The first step has mercury and then two sulfates, ether. And then the second step is the NABH4, and both steps are important, so you have to remember both of them and put a 1 and a 2. So these conditions will react with an alkene to get you the Markovnikov alcohol, which is the secondary position compared to the primary position. So this is similar to the methyl ketone product with the triple bond I was just discussing, because that used mercury sulfate, and then this, I mean, it's not mercury sulfate, but they both have mercury. So if the fact that both of the oxidizing reactions to give you the Markovnikov product use mercury helps, then just that's good. But remember, they're not the exact same conditions. Well, with BH3, it is the same conditions. I know that kind of sucks, but that just is what it is. Okay, so how can we get from here to here? Yes, so we have a secondary alcohol, so we are going to use SOCl2. We would only use HCl if it was a tertiary alcohol, which we don't have here. And then how can we get from here to here, final product? Probably draw it up. Yeah, NaCN. The solvent isn't as important, but both of what you guys put is correct. As long as it's not, well, even if it's protic, it would be okay because this isn't a good base, so we wouldn't have E2 competing. But both of the solvents you guys listed are good. THF is not protic, so that would work fine. Acetonitrile is not protic. DMF also works, or DMSO, or HMPBA, or HMPA. Acetone also works. Like, there's a lot of solvents we could use. What's important is the nucleophile is sodium cyanate, because we're doing an SN2 mechanism. Well, we could theoretically do an SN1, but I think this would be simpler. Okay. Last question. This is the working backwards one. So, working backwards from this product, what kind of substrate do you guys think we would have? Like, we used this reaction, NBS and water, to get that product. What did it react with to form that? I'm gonna number these two. An alkene between 4 and 5, yes. So this reaction is just, well, I showed you the products. It adds an alcohol and a bromine And it does that by reacting with an alkene, the carbon-carbon double bond. So, and it's important where the double bond is. It's just between the two carbons with the alcohol and the bromine. And then the double bond could be cis or trans. It doesn't really matter for this reaction, but if you look at the preceding step, kind of points out what it would be. I drew it as a trans double bond because these conditions are important. What is the preceding substrate from this? An alkyne, yeah, we're going to have a triple bond. Did I? No, that's okay. So yeah, Li and NH3 reduce a triple bond, an alkyne, to a double bond, an alkene, and they do it to form a trans alkene. So, like if you just worked backwards from this first one without looking at the preceding step, you might draw this as cis, but then you'd see this and you should know that it should have been trans. You just redraw it. I'm probably going to end up erasing something because it's just, I'm running out of space here. But what kind of reactant would we have that would be preceding this when we did an acetylide reaction? We just saw this in number 8. Just take off the alkyne and replace it with a Br. Yeah, so it does an SN2 mechanism, and it does that by reacting with a leaving group halogen. So and as Jared pointed out, it's gonna basically just put the leaving group in the place of where the triple bond and the rest of the chain was. So like this, because when this comes in, it attaches at that position and kicks out the bromine. So if you're working backwards, you can just think, well, that's where the halogen was, that's where the triple bond attached. So that should make sense. Yeah, I'm just gonna erase this, I guess. Sorry, I can't fit everything in on the same page. There's just not enough room on these things. What would be the substrate we react to get this product from PBr3 and THF? An alcohol, yeah. We're just doing an SN2 substitution to replace an alcohol with bromine. So just replace the bromine with an alcohol, work backwards to think like what it came from. I guess I'll erase this too. What would be the preceding substrate for this? An alkene, yes. So this set of conditions adds an alcohol to the anti-Markovnikov position. So the alkene is going to specifically be here. if you drew this, then the anti-Markovnikov alcohol would go here, and that's not what we have, so that would be wrong. And if you drew it anywhere else, that, I mean, even putting it here doesn't really make sense because it's specifically at the end, but just like the first thing you should recognize is these conditions react with either an alkene or an alkyne, but we have an alcohol, so we're going to have an alkene, and it specifically has to be this alkene to get the alcohol to be on that position. So, you know, a decent amount of reactions, but synthesis problems can only go in so many directions. So the stuff you see with the practice on Canvas and like the questions I just gave you, they're very close to what you'll see on your exam probably, because there's only so many questions he can throw at you. So that's everything I have. If you guys don't have any questions about the worksheet or material for your exam, then that's it, I guess. Before everybody leaves, okay, I see some people left already. Do you guys want a workshop on Dead Day, the Tuesday of finals week? Okay, that's one person, two people. Okay, so that's, just wanted to make sure. So I'll plan on doing that. Do you want a workshop next Tuesday after your final? Because I don't know what I would do for that. I guess I could just start reviewing. Probably not, yeah. I mean, I don't know how many people will come because I know you'll be sick of OChem after an exam. At least one person will come. Okay, I mean, having way too much fun. I don't know if that's sarcasm or not, but I enjoyed the class myself. I'm glad some of you are enjoying it.